Okay, this is part 7 in my devlog about RealtimeSwift, a declarative video rendering engine that I've been working on for the last few weeks. Since the last video, I've made progress on the two last big foundational parts of the framework, which are layout and animation. So, I'm Michael Forrest, I'm an indie developer working on Shoot Pro Webcam, Video Pencil, QCam Presenter, and other stuff on Squares.tv. So let's start with layout. So in Chris Eidhof and Florian Kugler's book, Thinking in SwiftUI, they say that we can imagine each view has a method like this, basically size that fits in a proposed view size, where a proposed view size has an optional width and height. I'm not going to go into loads of detail on this stuff today, but I'm just going to tell you how. I'm going to show you code where others can't because it's inside SwiftUI. But so I've started with this layout element protocol, which lets me then sort of like define that size that fits function and take this proposed view size. So that's the starting point for everything here, is sizing things. So then this implementation is sort of sprinkled throughout my project. So in every view that needs to be part of a layout, I'm kind of I'm sort of like bringing that into the sort of stuff that it needs to be in. So this, there's different sort of levels of complexity to the implementation of this. So I'll show you a fairly sort of, complicated one. But really, this is my generic. This is sort of my container view that has a size that fits a proposed size. And just basically supports horizontal or vertical axis by sort of taking a list of sizes and reducing those by either adding the widths together or adding the heights together. So, it's not amazingly complicated, but like, it's just like adding a load of widths together and putting some spacing in between them. So that's all we're really doing here. But what's important, something that was a real breakthrough for me was that layout is based on the attribute graph, not the resolved view tree hierarchy. So I'm going to say what that means in a sec, but that's why we get a reference to the graph and we look for the edges that relate to this view, and we grab we compute each of those sizes of the views, and then we kind of lay those out to figure out the size that fits. So we're traversing the sort of the view. I'll show you what I mean now. So this is what a resolved view tree looks like. So once we execute body on whatever bits of our code that we need to figure out what that view is, and this kind of resolves it into a stable structure, right? So this is a real-time VStack, so we see that kind of coming in here. We see this real-time for each, and then we see that is represented here as like a for each, and then we see the explicit output of that as individual nodes now. We've got this text layer which shows the current date, and that's kind of coming through up here. But then, when we've got this if presentation timestamp, so we've got a conditional things, and then there's an optional view there, which is a kind of resolved view, and then we've got the actual content of that underneath. So that's kind of like what we're resolving the code into so that we can do diffs against it, so I can compare one to the next. Okay, so this is what the attribute graph looks like. So where here we have this kind of nested structure, here we just take this, the presentation view is the top level, and then we've got this VStack, right, which goes to here, but everything else has just been flattened out into nodes that all sit under that VStack, and that's like that's something. We're doing something here, right? So and this is the result of that. So the VStack can just take each of those views and sort of lay them out with consistent padding between them, as you'd expect. That's the way SwiftUI works. It's the way we want to do it. This is my debugging tool, and I'm going to show you a bit more of that later, but it's been really useful for me to kind of figure out my thinking and also explain it to you by sort of making this feel a bit more enjoyable to use. But yeah, the flattening logic there, where how am I kind of turning that kind of nested hierarchy into something that makes sense as a graph that I can then start rendering. But it was hard to figure out. And then the key really, I had a weekend of having headaches, and I thought, it's time to get some unit tests in here. Come on, Michael. So you should know better. So the first step of getting these unit tests together was just sort of making it so that I could output a description of the tree and the graph. So we've got tree descriptions, we've got graph descriptions in here. So the tree description here, I can have IDs or not. Then IDs are really useful sometimes for debugging and sort of figuring out exactly which view and sort of putting a breakpoint in on that exact view's ID so that I can follow through exactly what's happening. This has been amazing. This I can render out what that resolved view tree is. So in this case, like this is actually like it's a real-time Z stack with a view pair, which is something I defined down here, which is just 2 text layers, but just to test how it kind of works with a body call. So you see we've got a view pair, and because that's in a body flat, that gets a tuple real-time view, view 1, view 2. And this stuff is all the view tree is all important for like figuring out the IDs of things, so that we can do those diffs. But here you can see some of the different cases. So like here we have quite a complex resolved view, but actually like the output needs to just be that. So I had to figure out how to like make this come out of that, right? And similarly, like something like this where we had a Z stack, and then I've got a hello, and then another Z stack, and then a thing, and then another Z stack, and then a nested body, right? So okay, let's see what that looks like, and this is what we expect it to look like. And then that was complicated, and so each sort of like complicated situation I'll make a view test for. Just not too many tests, just enough to kind of like sanity check everything. Modify, like, so I've got an overlay here, overlay modifier, and I want to make sure that that turns into, and this is interesting because this is like modified real-time content, overlay modified view, and then that lays out its 2 subviews, and then that's sort of actually kind of like should shake out to the same thing in the view graph, because that thing needs to still be there, like manipulating things. Like we've got the for each test here, like making sure that when we've got a for each and then outside of that a view, that we want all of those to end up in the same hierarchy at the same level, or we've got nested stack, and so this, you see they sort of get, this has got a Z stack with a text layer, and then there's an overlay with another thing in it, so I'm just checking that that kind of comes out as a Z stack with the overlaid modifier. So these were things that in my initial versions of the code didn't quite work as I'd expect. So this kind of flattening logic all kind of hinges on this, should something be flattened by the container. And we basically, one breakthrough for me was if a view has a body, like it's not really relevant for that. That's an implementation detail in our code, that we want to break up our views into different types, but like the renderer actually kind of like wants to undo all that and just put it into a flat hierarchy. So if something's got a body, then yeah, it should actually be flattened out, and those bodies usually are made of tuples, and those tuples should be flattened out as well. So then that's what we've got here. We've got this flattened by container protocol, which starts with tuples, tuple real-time views, where it sort of creates a sort of collection of different views of different types. If something's a conditional, if we've got that if body call in there, then that's something that needs to be flattened out. If it's this is like the modified real-time content, I'm not sure I even need that, but the for each is like it needs to be flattened out once we've figured out what's in there. So yeah, this is kind of like, it's not crazy. Like this is something that's quite easy to think about, whereas like the bit where I use it is a bit more complicated. So if it's a container, we're sort of flattening out the children by sort of going into this flattened children and looking at should it be flattened. I sort of confuse myself. This is why those tests are important, because this gets pretty hairy because I'm sort of traversing the view graph, and sometimes I will descend into the children looking to flatten out the containers, but then I need to make sure that I've still got this list of invalidated nodes that I'm iterating over. So each of these, this is called by this is sort of iterating over the changes, which are going to be the IDs of everything that's changed. But I've also then got to make sure that I'm sort of like keeping an eye on what I've already dealt with, so that I don't end up with like duplicates of stuff, which was happening a lot, as like traversing into the children and then getting duplicates of the things that I'd already kind of dealt with. So it's not the simplest thing, but I'm not going to go into great detail on it. But the important thing is I've got tests for it, and we can like talk about the content of those tests and then kind of make it conform to that, and we can iterate on how that implementation works. But I think like the arguments should be about, are these tests, is this how we want it to flatten out actually? And then we can like deal with the implementation. So we look at the graph, not the resolved tree. So that was something that took me a while to get my head around. It's like, what am I looking at when I do these layouts? But it's that kind of flattened out view hierarchy that we get with that we create once we've kind of like figured out which things that we've got to do. Anyway, I thought we were talking about layout. So how does that work? So this is something I've been looking at a lot. This is Thinking in SwiftUI, Chris Eidhof and Florian Kugler's Objc.io book. It's the layout engine of SwiftUI does some stuff. So I'll follow you through this. So actually, like when you're looking at these views, you've got to think of it almost like if you've got a modifier on a modifier on a modifier. That the last modifier is like at the top of the hierarchy. So you've got to think sort of upside down. When you're looking at these modifier chains. So that's why the background is on the top. And then, so what we do is we go, okay, the background is this size, and then we sort of subtract the padding from it. And then when we go down to text, the text just goes, no, actually, I'm just like this size, the size I want to be. And so we sort of go back up, and now the padding goes. So it's like the text has an allocated size that it is allowed to fit in. So the text will, well, it will. If this is small, then the text is going to have to sort of maybe like wrap onto a new line to fit. So then it's going to report back the size that it wants to be, and then that padding is going to get added back on, and then now the background knows what size that it's going to be, and then it can make the color the same size, right? But yeah, if the text is just small and you've given it loads of space, then it's just going to report its ideal size. So this kind of like this node traversal thing is interesting. It's something I'll probably need to go into in more detail. But actually, like, I'm not sure. I think my needs might be a bit simpler. So this is another video I've spent a lot of time in, which is SwiftUI Under the Hood. This is another video on YouTube where he really sort of like shows you that layout logic in great detail. So if you're interested in the layout stuff, really have a look at what Chris Eidhof's doing. But yeah, so this is where we are. Like the first thing we're going to do is compute the view sizes. So that happens either in the view updates, or also the first time that we instantiate our renderer. So for each change, we're going to do this compute view sizes. Right, and we start with the size with basically 1020, 1920 by 1080 is what we want to fit everything in, because don't forget we're making video here. We're not making arbitrary user interfaces here. We're trying to get something that can be turned into a video output, a live video. So that's just our needs are slightly different. We're not highly interactive. We're not doing buttons and stuff here. We're doing we just want to kind of layer up some stuff. That's sort of like the first part of that. So the layout element is kind of the size calculation part. And the other key protocol I've created is compositor. So that's the thing that then like applies that layout. So compositor takes an input dictionary of images, and I know the identity of those images, and I output an image, a core image. So these compositors are created as part of that insert or update function. So when we're kind of like hammering out that node graph, each of those nodes in the tree has a kind, and that kind then encodes what kind of thing it's doing. So a compositor, if that node is a container, then it's going to probably supply a compositor so that later on we know how to put it all back together. So here, for example, so once an implementation of that is in our like stack compositor. So you saw the container size calculation. Now, how do we actually like do something with this? So there is like to some extent probably a little bit of overlap between the logic there that I don't know. I'll figure it out. Like this has been very difficult. But yeah, this is what's happening here is we're starting with a frame which starts at the origin essentially, and then we depending on the direction of the axis, we're either kind of like offsetting a transformation by the x coordinate or the y coordinate, and then we are applying a transform in core image, and then we're compositing over the result. So in core image, you don't like glue two images edge to edge. You like each time it's a composite operation. But don't forget, like core image is just like storing all of those operations required to make the final image, which only gets created when we call render. But also something to note here is that we're dealing with a different coordinate. So our views, we're kind of thinking in terms of top, whoops, very bad box, like top to bottom, right? Sort of going from the top left essentially. But core image actually starts from the bottom left. So the way we have to do it is like, okay, we start at the top. So this is like height. And then first we offset by the frame that we've got. And then when we render that frame, that's like rendering in from like the bottom corner. So this is like the origin of each thing that we're adding. And so that's why when you look at this, I do first I move the frame, then I render the child image. If it was the other way around, then we do it the other way around. And that's something that I noticed some bugs because I hadn't realized it straight away. But yeah, as I say, the great thing about core image is we can actually put a breakpoint in and see, like, okay, here's the result image, and I can actually have a look at that, and it's got this visual debugging thing. But it can be a bit complicated. So, you know, like as we sort of like look through this, we see like that this is actually not for a particularly complicated view either, but, you know, we can see it's got like our image. So because I'm working with images in this particular case, where are, I think, yeah, so I think it actually makes CG images when it's doing the text, and then it does a bit of color matching. Here's our transforms, that affine thing. Here's another transform by 84. And then we've got these source over. These are the composite operations, but it is a little bit complicated to think about. So that's why I started tracking these changes as part of my own debugging tool. So this is my tool where I can have a look at, can we zoom in a little bit? Let's crop in a little bit and save that. Save zoom. Right, so this is my tool. So here I can like this is the video preview is over here. And then here's the graph, and here's that kind of like resolved node. So I can sort of like have a look at, I can sort of select the resolved nodes, and I can kind of like sort of move these around so I can sort of like get my head around it. In this case, because we're dealing with this like vertical alignment, I thought, well, let's just sort of arrange these top to bottom. You can see the IDs in here, and I can like copy the ID if I want to sort of debug that. I can I even like messed about. I was like, let's make it so I can like align these nodes and stuff. So this is like my debugging tool, but something that's really useful in here is I can look at, okay, well, what's this node rendering out as? Okay, it looks like that. This one, okay, this one looks like that. This one looks like that. And then when I look at the kind of V stack, I can see what that output looks like, and then I can see that that's getting composited in. So this is yeah, like it's just, this is a debugging thing. This obviously, like the runtime isn't going to be caching all these intermediate images, but it's really useful for me figuring out the framework and also figuring out my own application code to have this. There's a timeline down here which we will get into later. But so that's layout. So basically, we compute the sizes of all of our subviews, and then we compose those images using core image. And so the size computation happens each time the tree changes, any part of the tree changes. So even though we're not rendering body on everything for the whole tree when one part of it changes, we do need to recompute those sizes when any one part of the tree changes, because say some text suddenly gets really big nested down, that's got to like have a chance to propagate back up and affect the rest of the view. So the other thing is yeah, composing images, that happens every frame. So we're sort of like constantly rendering, and that's, you know, that's just because ultimately, this is a video tool, so there's going to be new frames every single frame, right? There's going to be new images every frame, so that we're doing. But remember, like, our constraints are slightly different. 30 frames a second is actually not that bad compared to 60 or 120 that the operating system is doing to give you a user interface that feels interactive. Like a video is 30 frames a second, which is actually a pretty long time in those animation terms. But yeah, let's talk about animation now. So, and I know this video is already 20 minutes long, and I could have broken it into 2 videos, but I thought let's just do it in one. So I've spent a lot of time in this particular video, Explore Swift Animation, and this is by Kyle Makuma. it's got some great diagrams that you'll maybe notice like influencing how I'm like visualizing things in my own debug view, right? Because it's been a really like clear sort of way of sort of looking at things. So this is one I've watched 3 or 4 times probably. Harvey first thing, and we get up at 5:30, and I sometimes stick one of these videos on the TV, and the toddler enjoys when the example has pictures of dogs in it, so I get away with it. But yeah, the heart of SwiftUI's approach is this animatable protocol, and it's the same approach that I'm taking with RealtimeSwift. So anything that's animatable conforms to vector arithmetic. So it has an animatable data property which conforms to vector arithmetic, and this means that values can be like subtracted from each other. We can compute a difference of any sort of set of values and interpolate those along the curve, right? So we can say we're here, right? All using this single generic implementation. And so there's a lot to talk about here, but I'm not going to go too much into it because Apple have covered it. But a key insight from this particular video that I just mentioned was the way, and a difference between the way I was thinking about it before I watched it, was the way SwiftUI tracks the model and the presentation values. It's not sort of going, okay, start here, end up here, how close are we to here? Each time there's a change, it creates a new animation based on the current, so it computes the change based on the model value, right? So it gets a new value and it goes, okay, what would I have to do to get the model value, which is like the stored real value, to the value that it wants to be? And we compute that curve, but we compute the change, right? And that then, the amazing thing about that is you can then have 2 of these animations, both that have calculated the delta, but if they run at the same time and combine, then they smoothly like combine together, and it's really cool. Like it just automatically, you sort of smooth out these easing function based animations. It's not something I'd ever tried, after 20 years of doing this stuff. I haven't really done my own animation functions for ages. Like when I was doing ActionScript, it was all like get the easing functions. Is it easing out quad? But since I've been like on Apple platforms, they kind of handle that so much. But I love this, right? You store the delta and then you just like add those animations up and you kind of get the right result, and it's really cool. And it was actually really easy to get working. So my project, just to get into the specifics of what this all looks like in my project, is Animatable. And then I've just called it like real-time vector, real-time animatable. And this is actually, so if we kind of look in like what real-time vector is now, this is the only place in RealtimeSwift that I have a dependency on SwiftUI, other than SwiftUI-based debugging tools, because I just didn't want to re-implement all this boring like vector arithmetic stuff. Like I could like go in and have my own. Oh, it's not coming in. Can I have this? Are you gonna? That's weird, isn't it? Loading the standard library failed. Like, Xcode bugs, you love it. So I didn't want to like re-implement this stuff, but so I'm just like using it for now, and so it's got this import here, so that I can just like, but I'm type aliasing everything that I am using. So vector arithmetic becomes real-time. It should be called. I just didn't want it to be long. Animatable pair becomes real-time animatable pair, and then. Yeah, so obviously, like the project also has for the debugging tool, that's SwiftUI as well. But like the nitty gritty stuff, maybe at some point we want to just be completely free of SwiftUI to be cross-platform or whatever. But this is the only place that I'm really relying on it. And so this is how we use this is our animation modifier, right? So we're going to be able to call on real-time view animation. So I'm not going to have like with animation call. I'm just going to have animation modifiers on different parts of the view hierarchy. I think the with animation tool it's like I'm going to click on a button, and it's sort of like an easy way to do it. But actually, I think for my purposes, for RealtimeSwift, it's like you're always going to be in this kind of video composition. So we're always going to be going via the animation modifier. But actually, I haven't actually done anything with this yet, because my persistent node update function, just like so this is kind of called when when this node has changed, for whatever reason, it gets this update call with the new resolved view to figure out, and a timestamp to figure out what to do. In the moment, I've just kind of hard-coded in a transaction each time something changes, and I'll figure out how to kind of like propagate these transactions later and where to make them. Yeah, what I'm doing is I'm kind of creating this transaction here and then like figuring out what kind of node and doing some stuff, which I'll show you in a sec. But here's Chris Eidhof explaining the animation transactions progress. So you see on the right, if I just get out of the way, you see he's sort of like it's showing how it kind of goes down the tree, and sort of when it finds something animatable, it will kind of apply that animation. So we've got this transaction, and then we've got animatable views, and then they just need to then, you know, if something is animatable, so I think it's the so if something is animatable, then that's kind of what that looks like. We update it, but I'll show you that in a sec. There's also this some stuff about the transaction in Apple's video here. So like but this is talking about sort of taking control of the transaction in the view hierarchy to achieve different effects. But they do talk about this transaction that sort of goes. I think I've got this like invalidated IDs concept, and I think this is going to end up being the transaction. Like, how do we so instead of this is a binding on real-time render. So it's a set that just kind of lives all the time on real-time renderer, and then is bound to is bound into the current tree. So when it's first created, it's bound in there, and then when a new tree is created from the existing one, those bindings get passed through. But I think probably instead of having this, that's probably what the transaction is. So that's something that I still need to just cement. Because I'm just focusing on getting the animation itself working. So currently I'm only implementing animation in modifier nodes. That's kind of where I started. So you see, when we come into the modifier node, we've got this image modifier type. So if I have a look at this modifier thing, we've got this any image modifier type, right? So this image modifier has a render image function, which takes an interpolated value, which has this view animatable data input, right? So this is like anything that can be animated conforms to this image modifier protocol. And the same with audio, right? We take the interpolated value and we do something with it, and we know what the module is. But yeah, this is we take the interpolated value and we do something with it, right? And then here's how that looks in the opacity modifier. When we get this, so we've defined animatable data as just a double, so it's sort of the simplest case really. And then when render image with the interpolated value, literally that's just a float now. So opacity is interpolated value. And then if we need to change the opacity, I've got this, I've just got like a filter that we put the opacity in one of the vectors in one of the axes, and then we return that filtered output image. So that's, we're taking the interpolated value and we're using that to animate. So you can see that we're going to be doing that in a lot of different ways in different types of situations, different modifiers, different views as well, probably. And yeah, again, the view conforms to real-time animatable with this animatable data, which is of type double, which conforms to vector arithmetic, because I did that. I did that here. So CG float. Do I have double? I'm sure I've got double in here somewhere saying just conform that to vector arithmetic. That's just inheriting it from SwiftUI. And then we do, the core image filtering, and that's how we get that image out. But if we come back to the update function, this is where the animation actually happens, right? So this is a frame-by-frame update at a specific time. We update the value. If it's if it's animatable, we can update that. What is this update function? I haven't got my generic types propagating into this persistent node store, so I'm taking actually an erased value into here. So this is just any. So I'm just like, okay, this is like a kind of seam in the implementation that doesn't sort of enforce generics and stuff. But basically, if the erased the erased it's erased, but then we just make sure it conforms to our extensions, like our animatable data thing, and then we can call update on that, and then the update does, which I'll show you in a bit. But like actually this part was probably the bit that I kind of spent ages getting confused by, and ChatGPT wasn't really helping, this erasing to any, and then because something that I had to get my head around is we can extend animator. So animator has an associated type of view, right, which is an animatable view, and so we can't call update without knowing the type of that view. So we can't call its update function animator update without knowing the type of its view, right? So I can't just call this from my code from outside without knowing the type. But we can create an extension on animator that doesn't like have to know the type for the function call, but inside here we still have access to that generic type. So it's like it's quite, I still find it a little bit weird, but like once you kind of realize this, a lot of things come into focus, and in a way that like when, you know, ChatGPT, here's a diff from like, it was I was supposed to be going to bed, it was 10 o'clock, and I just was like, I think ChatGPT has sold me some unnecessary abstraction, because it's sort of any image, right? It made me do this any animation mod. At first it wanted me to do one for each type, but like any animation modifier was like, it was like, okay, make an animation modifier, any animation modifier, and then pass, and then when you construct that, create this update function, which is then attached to your struct. And then I was like, oh, well, so to do the same thing with render image, I've got to like make two functions, update those. And I was like, what the heck is all this? And then I realized, like, no, I just extend the I just have to like extend animator and have this type erased any, and that's all that this is doing, is just like kicking that type erasure down the road into this nested struct. So just watch out for, like, if you don't really understand something properly and then you end up using some code that ChatGPT has given you, you like, it does have a tendency to want to put extra layers to just like keep abstracting things up into more and more types in a way that, but it's always just like pushing that key piece of information further and further down the road, and often still not solving the problem. Like it'll be like, here, just wrap it in this. Oh, just wrap it in this, wrap it in this. But at no point does it realize, like, no, the key is, no, just make this type erased or extend it from a different extension, right? And it's all going to work. And we're just doing that inside a thing, inside a thing, inside a thing. And it was just loads of unnecessary code. So that's just like coding with AI when you don't totally understand what you're doing. It does lead to that sort of rubbish. So then, you know, I was glad I managed to, like, you know, this was me. This was all the stuff I did to correct. This is one diff. This is just me removing the complexity that ChatGPT introduced once I'd had a chance to think about it and understand it a bit better. So once we're inside Animator, we can cast to the generic type and call update. So here we're going erased as view.animatable data, and like just call this update. So the implementation is actually pretty simple. If we find an animation in the transaction, so we've got something to go on, we can now figure out the change for that animation. So our view hierarchy has just changed, so now we've got to animate to the new state. We just can take the target value and subtract the model value, because we're implementing vector arithmetic, and this target value could be like 6 different fields, right? But we just get that delta, and now we just give that to a real-time running application struct, animation struct, with the transaction, the time of the transaction, which is going to set the start time of this running animation, and then just grab the duration, grab the curve, just copy everything into there, and that just like is just, we can keep a set of these values, which just gives us start time, duration, curve, delta, right? So The struct is then responsible for interpolating between the two values. So again, like we figure out where we are, like how much time has passed. If we're past the end, we just return the end value, the change, right? And or otherwise, we just like, here I'm just like casting that CM time. By the way, I'm working with CM times because I want to be able to think in terms of video frames, and CM time is really great. I explained that in an earlier video. But yeah, so we take the progress, so a time between 0 and 1, progress through the curve, take that curve value. This is just like implemented by SwiftUI. It's just there's a unit curve type that does this. You could bring in any number of easing functions to do it yourself. And then we interpolate from 0 to that new delta value to get the interpolated value at that particular time, right? And then I'm going to skip over the node rendering part, but just this happens every frame. But what we see here is if we've got a modifier, we get this image renderer, and then so each time we render a frame, we can call render image at this time, right? And then what does that do? That comes into this, so this is just a generalized thing, image modifier. And then what this does is just takes all of the animations that are attached to this view and just add them all together. So we take 0 and we just add that to the next interpolated value. So we're combining these all together, getting a final interpolated value, and then just calling render image for that specific type with the interpolated value of the right type. And that's going to give us our final output image. And then I'm actually when I'm debugging, I'm actually holding on to all the animations that have ever been applied. Otherwise, I'm just like clearing them up if they've all finished so that we don't end up with like a load of expired animations. So yeah, and I'll show you how that plays into the debugger later. But here's my a side effect modifier. So I'm going to just show you this. Hopefully it's going to find it. So this is the... This is, am I in the right one? Where's my real-time progress testing view window? Right, this is it. This is results time. Let's zoom in a bit. Let's just crop this nicely so that I can see it perfectly. And I'm going to save the zoom. Right, I've made myself a little test harness. You can see the view hierarchy here is a bit more complex than other ones. But if I hit toggle, whoops. Hello, and you see if I sort of press it fast, it doesn't there's some hitches, but I think that's like the UI. You see it doesn't go all the way up to the top if it gets interrupted. It sort of like slows down and comes back into the other one. And because this is all, I'm holding onto them, I can actually see all of these animations, and I can even I'm so happy about this. This was the last thing I did yesterday. I can actually run through those animations again and have a look at them. So how fun is that? It doesn't update. It should update this and this still really, but for now it's just cool. I would have killed to have this kind of debugging tool for all the work I've been doing for the last couple of years on QCam. But I can also here I can see how these things are combining over on the right if you want to have a look. So here's my overlay view. Here's my sort of source views. So it's like a test card, and then I've got my video pencil fake view, and then I've got what does that look like when they're combined, and then I can see okay, that's now in there, but then now we've got this layer which is the full size and it's got the thing in the corner, and then that kind of gets combined into a Z stack into this final image based over my camera. So you can see this is how I'm going to be perfecting my animations and transitions and really getting QCam looking great, and also being able to spin up other apps as well. That's going to be fun too. So I'm just actually going to, before we finish, I'm going to show you the aside modifier again, because it's not actually as simple as the opacity modifier. So this is the chronic case of vector arithmetic. So aside effect config corresponds to that real-time vector, that's vector arithmetic, but it has corners and it has opacity, but then corners is a combination of 4 CG points. So and then for each of these, and then I've just crudely done, I think actually the robot did this. I could probably make this better, but to add them together, we have to add all of the elements. And so that's kind of how this all works. This is what 0 is, just everything 0. And And then I've got like bottom left, bottom right. This isn't implemented yet, but like I've got different set of points for each of these, and then the opacity is this. Or if we're sort of full screen, then we're top left, bottom right, and opacity 1. And you can see the interpolated implementation here as well. So like this is kind of what it looks like in the most chronic case, and that's kind of how we can still get away with just doing target value minus model value. So all that just gets boiled into this. So isn't that great? Like, and that's probably about as complicated as things are likely to get with these modifiers. But you know, fun time. So I need to like quit and bring that back for the timeline to start running again. But like, how cool is that? Like, we're able to do these animations. So I've actually got this on a private GitHub repo now. So feel free to reach out if you want to talk more about collaboration, because I'm not quite ready to make it public. There's still loads to do. I'm really focused on making it work for my project as well. So, but if it's something that you think you would benefit from or want to be able to contribute to, I've figured out how to get that on its own GitHub repo. Git subtree push. It takes ages every time, but at least I can sort of extract it from my project whilst not like having to like do extra Git commits each time I push my own app. But yeah, that is where I'm up to with animations and layout stuff. So the next thing we talk about is I made this video using QCam Presenter, and here is what the script looks like. So this is, I've just done it. It was 2 takes because something went weird halfway through, but I'm going to stitch them together. But I basically write a script in this tool. This is the app that all this work is going to go into. You can get it from qcam.app. So I can put together my script. It's got this markdown syntax for titles. I can sort of make different layouts using the different buttons like this. I can paste images in and sort of like move those around. I can jump to an Xcode screen share, which you'd be able to see if that was there, and I can tell it to go to a specific line of a specific file if I want. Like this is going to RealtimeSwift something line 101. So you see all this thing just allows me to create these videos in one take. Takes me a bit to assemble everything I want to say, figure out what I want to say, but actually when it comes to recording it, it's pretty quick usually. And this is my setup for filming. So I've got like a teleprompter here, so I'm just reading my teleprompter as I talk to you. I've got an iPad down here which I can draw on things with. And then like I'm sharing this screen here, and then I've sort of got some other stuff on this screen, and then my camera's in the back of the teleprompter. And this is all just like running through QCam Presenter. So you can try QCam now, qcam.app/download, and it's going to be getting really great soon. I noticed today I changed I finally made it so that you can customize the padding, but I don't like this default lower third padding that it's given it. So I'm always tweaking it. Thanks for watching, and you know, feel free to reach out if this is interesting to you. I'm pretty easy to find. Cheers. Take